Okay, so in this video we're going to look at how to solve equations using the TI83 or 84 um, and answering questions that we have about a given function scenario. So here we've got a function between the time in years t it will take to retire as a function of how many dollars per year I save on average. Right? So we could say that the amount of time it takes me to retire it depends on how much I save per year on average. So if we say that I need $250,000 in an account to retire, and most of us are probably going to need a lot more than that, so let's just say it's just one account, that the amount of time is modeled by this rule here, T equals 250,000 over D. Again, where D is how many dollars per year I save on average. So some of the questions we might have about this account. Let's see. How long until I can retire if I save, let's say, $5,000 per year on average? And let's say, what if we jack that up to 15,000? Which I believe somewhere around 15,000 is the most you can put into a 401k each year before having to open a new account. But anyway, those would be two good questions to ask. And how about as well, what amount of money should I save each year on average if I want to retire in, let's say, 12 years? Let's say that's on my plan. Now again, this is really simplifying things. We're not taking into account interest, anything like this. This is just raw dollars. So it's not totally realistic, but it's a good ballpark, and it'll show us how we can solve equations using the TI84. So let's look at the first one. How long until I retire if I save $5,000? Well, really that's going to be using this formula, and I'm going to be substituting in 5,000 for D, because that's my input, right? D is my input, T is my output, D is independent, and T depends on D here. And so, we can go ahead and calculate what this would be. This should be around 50, right? So if I save $50 per year, or sorry, if I save $5,000 per year, it will take me 50 years to retire. Again, thinking that the units here, input of dollars per year, units here are going to be years. If we verify this with the TI84, what we'd do is we'd come up to our y equals. This is where we input functions. And our calculator has to keep things general. So it doesn't see things in terms of t's and d's like we do, because this is nice for us to keep things straight. It sees things in terms of y's and x's, where y depends on x. And so this is just for the calculator. So when I come up here to y1, this is what I'd type in, 250,000 all over x. And it would be worth our while to think about what the window should be here. Again, we can't really pinch and zoom on the TI84 like you can on Desmos, let's say, but it forces us to be mindful of where we want to view the graph. So if we think about it, we're going to be, dividing 250,000 over a number of years. This first calculation I came up with seemed to be, mapping out for a long while. So I want to keep my x min, my x max, so my input min, input max, and output min, output max are values that we're going to want to set for the window for graphing. So you can typically use common sense, meaning what we understand about the problem. So, having negative years or negative amounts of money being put in probably don't make sense in this context. So what's the input? Input is D. and that is the number of dollars per year on average. And so what would be a good input minimum for that? Well, maybe 0, maybe $10. Maybe we don't want to start at 0, but let's start at 0. Let's say the most we'd solve or save might be 15,000. Okay, and there's some flex in here. These don't have to be one particular value. It depends on what you're looking for. And then our output is the amount of time in years. So a good minimum would be maybe 0, and a good max might be something like 50 or 60 years, right? If you start working when you're 16 and you make it to 76, that's a good rough estimate. And again, you can play with this depending on what you're looking for. And so we do that here. And again, instead of d min and t min, we're going to use x min and x max. So up here we'll put in 0 for my x min. My x max is 15,000. Don't worry about scale for now. And my y min or t min also 0. And the max might be, oh, not 600, 60. And we'll take a look at what this graph looks like. Okay, and so we have here, this is called a parabola, or excuse me, this is called a hyperbola, and it's an inverse relationship. So you notice that as d increases, t decreases, right? So as I read this graph from left to right, as my d values are increasing, and we always read graphs left to right, that t is decreasing, and not at a constant rate. It seems to be kind of tapering off how much it's decreasing over time. So that's kind of interesting. So, but to get back to our original question, how long until I can retire if I save 5,000? Well, one way we could look at this is by going to the graph or going to the table. So if we come to table set and we start at 0 and we go up by, let's say, $500 each year, because that's my input. So starting input and then the change to my input. We can do it like that, and we'll come back here to look at some other options. So we can't save 0. That relationship doesn't allow us to do that. But if we save $4,500, we're noticing the output would be 55 years to retire on time. If we saved on average $10,000 a year, it would take us 25 years. So these are these input-output pairs here. So this is great. So what we can do is we can, one way to get the answer for this first one, how long till I retire? If I say 5,000, well, that'd be 50. How about 15,000? Well, I can scroll down. Depending on what you chose, it might take a bit. So 16 2/3 years for 15,000. So let's jot that down. It will take me, how long did we say? 25 years? Or it was longer than that. $50 years, that's right. 50 years to retire if I save 5,000. Oops, on average. And 2/3 of 12 months is what? 8 months. If I save 15,000 per year on average. And that should go up here. Okay, you notice I'm using complete sentences here. They're complete thoughts. It's not just math jargon. I have units, and it's concise as well. And one of the biggest things that we emphasize in this course is clear communication of the ideas, because computing them is one thing, it's relatively easy to do in a lot of ways, and then rendering it into plain English to communicate this to other people, that's more of a challenge. That's where our focus lies. So never being pleased with just, the answer of 50, right? What does that 50 really mean? Well, it means it's going to take me 50 years. Okay. So we've looked at graphing, we've looked at a table, but this can only answer kind of this question here. But my second question is a little bit more interesting. What amount of money should I save each year on average if I want to retire in 12 years? So this is a bit different. What I'll notice a lot of students do is maybe, kind of just scan through the table and try to get an estimate, and you'll just be like scanning all day. I want to get to 12, want to get to 12. But it's not going to be exact. We have some idea of where we'll be. Again, just looking over here to the output of close to 12, we're going to be around 20,000 or 21,000. But let's say I wanted to know, wanted a countdown, like down to the day, how long it's going to take. Well, there's two ways I can solve it. One would be to solve it algebraically, or graphically. I'm going to show you how to do it graphically right now. So what you're going to need to do is you're going to need a desired output, and for us, that desired output is 12 years. And you're going to put this into y. So we'll come up here to y equals, say, all right, this is my first output. My second desired output is 12. And what we're going to do when we graph this is see when this output crosses this output. If you think about what this should look like before we graph it, for all x, y is 12. So what's that going to look like? It's going to look like a flat line at 12. So when we come to the graph, we might need to switch this up a little bit. So what do we notice? Okay, my lines don't intersect in this window. So there's two things we can look at, but the first one should be, it looks like I'm not over far enough on my x, so I'm going to open up my x max to be maybe 25,000. It lets me look further into the graph, and then we see, okay, these lines do intersect. So that means this output does cross this desired output down here, and the question is, when does that happen? So what we can do is we'll use second trace. Second trace. Oh, 1 second. Second trace to take me to the calculator window. And they'll come down to intersect, which is number 5. And then it asks you to choose your first curve. You'll hit enter. Your second curve, if it's close by it, will guess that one, or you can navigate to it with these arrows. Hit enter. And then it'll ask for a guess. And so you can kind of scroll closer to where you think the intersection is. Doesn't have to be super close. Hit enter again. And then it will tell you where these two graphs intersect. And this is an approximation, but it's a darn close approximation. And so what we get is the pair x equals 2833.33, y equals 12. So what does this mean? Well, for my input of 20,833.33, I get an output of 12. What is my output? My output is the number of years it's going to take to retire. And my input is how many dollars per year I save on average. So what does this mean? If I save $20,000 on average each year for 12 years, I will hit my goal to retire at with $250,000. Okay, so this is a alternative way to solving this algebraically, and it can come in handy. The only things you really need to be mindful of are your window and inputting things correctly. And again, you can kind of use the table to orient yourself and get an idea of where you should be looking. That's all I want to cover for right now. So make sure you hit the class discussion with any questions.